So with much delay, I'm going to do lecture 7 now, which is representation of complex geometry. So this is a lecture that I've done for OAA and RAIC conferences. This is the one that I did in Ottawa, but I had done this before in previous years as well, or a version of it. Things updated and kind of improved. The idea here is that our buildings are getting increasingly complex, and we need a way to represent that. It depends on how your contracts work, but most contracts follow the kind of standard process where the architect and the engineers, depending on what scope it is, create a set of drawings, and then that goes out to various contractors and they bid on it, and then the owner picks which contractor based on the price, not depending on who the client is. Some places mandate that it must be the lowest, but some, if it's a private owner, it can be looking at the comparative costs and making sure they kind of grasped everything. So the idea is that those drawings, they should be able to build the building or project or whatever the object is from that set of drawings. So what do you do if you have something very complex? How do you relate that to somebody that they can take those paper drawings and build what you need them to build? My answer is that it shouldn't always just be that. And I'll show you why, but we still need something to be able to price things and talk about things and have an understanding of things, because we can't be expected to just walk around with a computer all the time with the information. We need paper drawings, or something that you can look at on a tablet, or something at a much smaller scale when you need to. So how do we bridge those gaps, and who owns that scope? Because that is a big problem I find on projects lately. So let's go through this. Let's look at why we need it. We're trying to convey 3D world information in a 2D format, and maybe that's not the best way to do it, because we've struggled with this for a long time. How do we take this information for, most buildings, especially lately, not U of T projects, but the majority of buildings are relatively simple in that they are some sense of square in plan, or rectangular in plan, or elevation. And that works really well in 2D drawings. But it's as we start to go beyond that. So this is the classic problem. How do we tell someone to build an orange? How can you do that? How can you describe that surface in some way? It's pretty easy to say build an orange, but you could look at this and there's some contouring in here, and your mind is adjusting that to say this is something round. But realistically, a contractor looking at this could take this and just build a flat circle. They could draw a circle on the ground, and they would have met the contractual obligations of this orange. So how do we then say, no, here's the skin that has to go around this object? How do we take this orange peel and describe it in a way that they could reassemble it into an orange? And that's the thing. We're not just miraculously producing a round orange. That gets a little bit easier with 3D printing, but we're still not at the level where we can use it kind of dependently or responsibly for structural scope yet. It's getting better. Even in the past 10 years, that's come an extremely long way. And there's different ways to tell someone to take those bits of orange peel and assemble them into an orange. And both are right. Both are going to give us an orange. And so who says one way is right over the other? And how do we describe that? So this problem has been around for a long time. Once we discovered the world was round, or discovered, then forgot, and then rediscovered that the world was round, how do we map? How do we tell someone how to navigate this 3D world, or talk about it, or explain it to people, this round surface? Obviously a globe is the easiest thing, but you then need a physical 3D object to look at. How do you deal with that? I just thought of a great Christmas present for my kids. Malcolm is obsessed with the world globe for boys. Sorry, if I don't write things down the moment I think about them, it's gone. So how did they handle this? We have computers and great fabrication information that we can use. So how would we do this, or how did they do it kind of throughout history? And there was a wide variety of ways to do it. None of them right, some of them partially right. So this is one way that you could do it. You can see that at the poles, it's taking wedges of this, and you can see that each one of these segments is actually representing the same amount of surface area. So you can see that this is a much smaller piece than this, both trying to represent the same amount. At the time, and this is 580 BC, most of the world's population lived right here. And so who kind of cared what was happening out here, as long as these bits were more or less related correctly to each other. So this was a smart guy. He calculated the height of the pyramids based on triangulation. So, we're starting to see people understanding these concepts of math. Hipparchus, who was a founder of trigonometry and a fantastic astronomer, also was interested in mapping the Earth. And here were two different ways. And again, these squares are all trying to represent the same amount of surface area. This starts to look very similar to what we see kind of in modern mapping. There's a few differences, but it's getting closer to what we would show kind of today. But look at this one, look at the distortion here. Look at North America relative to Africa. You can kind of see this little square. It's supposed to be the same as this square, or not square, but approximate square. This one, at least, kind of gave them all roughly the same proportion, but it really kind of throws off how it wraps at the top. We're trying to take something. We know that these aren't really this size, so there's something funny going on up here. This is kind of taking a cone and wrapping it out around it. We can start to see we have more and more methods of mapping it. Even Da Vinci, who kind of dabbled in absolutely everything, got into it. His was really great. His starts to look like that unpeeled orange, where it actually kind of took segments of it and then pulled it flat, and kind of coped with the fact that you would have gaps in between the math to deal with the fact that it was truly supposed to be round. You can imagine if you cut this out and taped it together, you would have something starting to resemble a sphere. A few more here. Now this is the Mercator map. This is pretty much almost exactly the one we use right now. Mercator didn't even know what he had stumbled on. He had created it, but everyone else kind of thought he was a bit of a kook until Wright figured it out and really kind of took off with it. So you can see that our squares start to get longer as we get kind of further away from the equator. Works all right, considering the majority of our population lives in this band here, where you can see the squares are all relatively approximately this band here, where you can see relatively the squares are all approximately the same size. Up here, where Greenland is, kind of drastically distorted, it matters if you're trying to kind of navigate a ship around there, but very, very, very little of the population lives up there. So it's almost kind of easy to forget about and think that that's happening. Northern Canada, very little of the population is there. I'm not saying that that's okay, I'm just saying that that's why this was such an acceptable map for so long. There were more. Still more kind of methods of creating more and more maps. So after 2,500 years, we still aren't getting it right. The best way to do it is actually have a round object to convey that information. And so if we can't do that, how are we supposed to possibly represent something like this? That's just a circle. This has so many varying curves and edges. How could we possibly tell someone how to build this? But yet we do. So there's got to be some compromise or some kind of groupings of methods to pass on that information. Between the kind of first and third time I gave this lecture, there was actually an award given to an architect who was an artist for producing kind of one of the best maps around. It would take a long time for people to get their head around using it, but the majority of the world's populated zones are in squares roughly approximately the same size. You can see Canada, which we're used to looking so much larger than the US, they look very similar here. And you could probably cut this in other spots, but they did it specifically here to try to keep the majority of land masses looking roughly approximately the right size. This won some kind of great artist awards. I don't know what they are. So Christopher Wren, who you guys probably all know, developed the modern method of architecture. Before that, the contractor was the architect, often also the owner, but not always. You might have hired someone very specific, but they were usually the engineer, the architect, the artist, the contractor. So kind of all of the roles in one. Wren is the one that said, you know what, everybody has their skill set. You want somebody who understands buildings to plan them. You want someone that understands, they weren't quite into having engineers yet, but they had help with some of that. We still weren't into mathematical based kind of engineering, so it was still kind of trial and error. So Wren would have had people helping him out with some of that stuff. But he would coordinate with the people that actually built it. So Wren kind of started kind of getting into organizing kind of descriptive geometry for buildings. So you can see here a drawing that he had done that really starts to let you build something intricate. Gaspard Monge, I'm sure I'm saying it wrong, is the father of descriptive geometry and differential geometry, but you guys probably don't care about that, but that's using kind of integrals and differential mathematics to describe surfaces and volumes. But the descriptive geometry is probably what you guys care about the most. I think he's kind of cool because he actually married a woman who owned and ran a forge. So, you know, he was the one kind of working with paper and pencil, and she was the one kind of managing the kind of really industrial works. But you can imagine that pairing working really well. And one of the places I really fell in love with kind of this complex geometry communication was through CastConnects, and I have one of their projects as a talking point later in this lecture. So what are the problems with descriptive geometry? We know we can do it. We talk about it all the time. We often talk about things in 2D from the 3D world, and we looked at a bunch of images. Often the problems are, if we are preserving length, we're distorting the angle. If we're preserving the angle, we're distorting the length. Both of those tend to lose context. Our mind is really good at isometric views, kind of seeing something from a 3D perspective and filling in the gaps, but that doesn't give us any real concrete information on how to build the object. So both of those lose context. But the big takeaway is that the smaller the piece, the less loss of data there is, but it starts to get really complex and difficult to convey that information. So you can see a man's head on a few different, or a person's head on a few different methods of descriptive geometry. And you can see, and the reason I like this with a person's head is that we have a really hard time accepting anomalies in representations of people. A dinosaur, a tree, cartoon drawings of that, we're like, oh, that looks so realistic and lifelike. Do it out on a person, and we immediately are like, that's weird and creepy, something is wrong, I don't know what it is. And it's also almost more eerie the closer we get to a correct interpretation of it. I recently heard someone describe it as the uncanny valley. So if anyone has ever watched The Polar Express, you probably know what I'm talking about. The people are almost too realistic, but still disturbing in the fact that things aren't perfect. The train, no more perfect than the people, but our brains can process that much easier. But slight imperfections in drawings of people, and we can't handle it. So that's why I like these images here, because it really shows us that even these two, which are probably the best ones, we can see are funny. There's something wrong with the chin on this one. And here there is a weird distortion, kind of where the middle of the face is elongated in a way that we wouldn't expect. This one, which is kind of looking more and more like the Mercator map, really helps illustrate what is wrong with the Mercator map that we know and love and use today. It's so much more apparent when we use a person's head to kind of represent that. So there are a few different ways to kind of illustrate or represent descriptive geometry. This is actually from a textbook called Outline of Theory and Problems of Descriptive Geometry. This was published in 1962, but I can tell you that when I was doing my courses in the mid-90s, that this was, it was pretty much the exact same book. There was very little modernization. Also at the time, 3D software wasn't coming along very far yet. We used a version of AutoCAD to kind of do our work, but it was still to show 2D drawings, so we weren't making use of anything of 3D. I'm sure all of you are pros at Grasshopper and Rhino and manipulating all kinds of things in there, but you need a way to be able to describe it to someone else. So you can see that we have a 3D object here that your brain is doing a great job at processing, but information is lost here. We understand what this object is, but it doesn't give us kind of measurable information. These three representations of planes do give us that information. So this was literally on my final exam. We were given this. I can't remember. We had to either go from this to this or this to this. I can't quite remember. But this one was literally part of my final exam in my graphics course. What I really like is this one. This one is maybe my favorite. This is what it takes. These drawings, all of these drawings are what it takes to properly describe what your brain processes right away looking at this. A segment of pipe cut off at an angle. So you can see it makes an ellipse here, that's represented by this drawing here. In plan, looking straight down on it, it would be represented as a circle. And here is a rolled out elevation of the surface. And so it would take all of these for somebody to actually create this object here. If you needed to give them information in 2D, that they could produce this image or produce this product, this is how they would need to describe it. So to really illustrate the different processes, I created when I was doing these lectures, a very simple structure that could help illustrate where the flaws are and why we would need these different views. At the time, I was very, very, very pregnant when I first gave this lecture. I was pregnant with Malcolm, so that's almost 5 years ago that I gave this lecture for the first time. And so I created Baby Bowick's Jungle Gym. So I took a sphere, and I created a grid over the surface. And what's really important here is you can see that it's not going to be perfect down here at the bottom. And I said, we're going to do an equal length dome structure and grids. And how do we represent that in 2D? So this is your isometric view. This is what I mandate should be on almost any set of drawings that have any sort of complexity visually to them. I find even when I'm working with architectural drawings, a rendering of the building is huge for helping me understand what the 2D representation is trying to convey. If I am doing a project that has any sort of 3D model kind of built into it, I will put it on the cover sheet, and I will say this is not for structural information or pricing information. It is purely contextual to help your mind process what is happening. So here is the intent. This is the jungle gym that we want to be able to tell someone how to build in a 2D drawing. You've got it. You see it right here. You understand what we're trying to create. But we need somebody to actually be able to build these objects and assemble them. So our classic method of representing that would be a plan and an elevation. Again, this still preserves intent, but on something complex, there's actually almost no measurable information we can give them. Intent is there if you're used to looking at things from 2D to 3D. You get better at seeing the back and forth between these two images very easily. But somebody that's never looked at something in a 2D way for a complex geometry or unique layouts would have a hard time understanding what this is trying to represent. This one is great because it is a true length plan. This is the actual length of every element in that dome structure, in that jungle gym. So this is the actual length. You could measure this, you could draw this to scale, and somebody could take a ruler and say, all right, this is how long every single one of these objects needs to be. Which is great because it shows you, when I described this as a equal length dome structure, it's hard to see that in this drawing and this drawing. It's really hard to see in this drawing. But this one really drives it home that they are all actually the exact same length. All intent is lost here. Is this being built on the ground? Because we could. This would be a correct way. If a contractor only got this, they could build all of these pieces and lay it out on the ground and say, there you go, check in the box, this jungle gym is built. It would be the most boring jungle gym ever. It would be more like one of those football exercises where you kind of run in the tires. That's about all you'd be able to get out of this. This preserves angle, which, depending on what you are trying to get out of the set, maybe not as helpful with our jungle gym set, but there are projects where knowing how to represent something to show true angle could be very, very handy. So this is representing the jungle gym, showing the true angle. But not all of the angles. You would have to highlight which ones were true angles, because you can't represent all of the true angles in one drawing. So these are these true angles. This drawing shows these true angles, and this drawing would show those angles. So you can see that we would still need several drawings to be able to represent our true angle plan. I really like this one. This one is the peeled orange option. This preserves true length and angle. So you can see that I created a grid network to be able to represent this. So these are the exact elements. I see you peeking over here. You're just.
I love it.
Have you ever seen me give this talk? I can't remember if you've ever been in the audience before.
I'm pretty sure that I co-presented.
No, you've never.
At OAA.
No.
Yeah.
No.
Yeah.
No.
I'm pretty sure that.
No, you were sitting in the audience.
Anyway, yeah, I've seen you with it.
Because remember the guy, the older gentleman talked about how it was so good that you were able to train me after the lecture, because Dave was sitting in the front row, and I referenced him because the Bowick Jungle Gym, and somebody came up to me after the talk and congratulated me on having Dave as a mentor to kind of lead me through this, to kind of tell me how to do my job, which was fantastic feedback at the end of my lecture. I was shaking with anger. Why are you giggling? That isn't funny. You should be angry on my behalf.
I am.
I know. He was actually very angry. He was very upset by it. So this one here I love because it's the unpeeled orange. Every length and angle is true. I wonder if any of you have caught on to the problem here. This object and this object are the same object. So there is a duplication of intent here. If this was actually just surfaces, this would be a really good way to represent this. You would end up with a somewhat segmented orange, but I could print this on a piece of paper and cut it along these lines and tape it up and have a sphere. But if I'm trying to build this out of stick elements, this stick element and this stick element are actually the same stick element. So we have a duplication of intent here. So we would still need to express that in some way. But we've got true length and angle in this drawing. So it's very, very, very handy. One that is used in multiple kind of methods, and in fact, Friotto really liked using this method, is contour plans, representing true height relative to the plan. So the gap between each one of these lines is the same amount. So we're going up in equal amounts of 1, 2, 3, 4, 5, 6 segments. So if we took the elevation and divided it into 6 segments, this shows you that the first segment goes up very steeply and that we start to go down in steepness. This comes into play in other structural scopes as well for fabric structures. So Friotto is kind of where this leads to, but Dave makes use of this a lot in his fabric structures, especially for representing the possibility of ponding under deflection due to other elements. So we've talked about kind of ponding on roofs and could lead to a strength, stability, stiffness problem. Contouring deflected shapes really helps us see that at a glance, once you learn to see that effectively. A really good way to pass on information to contractors, if you're trying to do it in a 2D world, is actually with grids, or coordinate points. These are all of the intersections of the jungle gym. Almost no context here. You can extrapolate almost nothing from this image. You can now because you've seen the 3D image, but if you started with this, you would have no context about what we were trying to talk about with this. But you give someone all of these coordinate points, you could do this, you could write it out in Excel and add it right to your contract documents. This would be a very suitable way where somebody could then take these 2D elements and put it into their own software and generate this jungle gym. Imaging with color can really start to be very handy to express, what you're trying to talk about. What I did with this one here is I actually converted the jungle gym into a reciprocal frame, which you guys just watched that lecture. You could have watched it 5 minutes ago, I don't know, but that was posted last week. This is taking the jungle gym and illustrating it as a reciprocal frame. So you can see that we have that segment here, that segment there, and that segment there, allowing us to kind of pre-assemble these elements that makes erection slightly easier. So we've cut the piece count down in half. So maybe all of these elements are what would be expected to be fabricated in the shop, that the contractor could then come to site and assemble them following this color-coded chart. Here is that same method shown in plan, allowing the contractor to possibly extrapolate some information. But we have a lot of other issues kind of embedded in all of this. So how do we build it? I mean, that last one helps out a little bit. How do we deal with tolerances? How do we talk about tolerance when we're dealing with these things in 3D? How do we check things? You know, it seems really easy to talk about, but trying to measure 3D points to 3D points becomes extremely difficult. In fact, Dave's project, the Canada Diversity Gardens that we've talked about, it is bogged down right now because the survey that's supposed to represent what is built doesn't seem to match what other people are expecting it to look like. And so they've spent a lot of time trying to unpack those discrepancies because the measured lengths aren't showing what the survey is trying to show. So how do you check these things? And how do you even allow maybe the fabricator to do checks even in the shop to prevent the problem actually arriving on site? You know, if you can find the problem in the shop, it's a lot easier to deal with than finding the problem when it's on site. So giving a contractor the means to kind of self-check before they even get to site is very, very handy. So if we had that drawing package for Baby Bowick's jungle gym, we would have wanted our usual, so for tender design development and construction, we would have needed general notes and a specification, typical details that show how we expect those things to go together. That often, so the general notes and the spec would have tolerance information in the drawings or in that component, what we expect the tolerance to be. Typical details show standard connections. We'd have an isometric drawing for intent. We'd have plans and elevations that also show intent in a 2D form. The true length plan starts to be very handy. The true length plan and layout and angles I find less helpful, but they can actually do measurements that they can check against in the field. It gives them the means to check those things. The contours, very handy to kind of just help check measurements as well. Node points, probably the most handy one for that if you're dealing with a contractor that can also work in 3D geometry. You'd be shocked at how many cannot work in a 3D world. And then we'd need assembly sections and construction details on how we actually expect these things all to go together. So I'm going to show you some complex buildings, and some of them are going to be case studies that I talk about. The ones that I'll talk about the most would be the Bergeron Center for Engineering Excellence, which I did the engineering for the facade, and we kind of broke some boundaries and changed the way documentation on a project works with that project. The template for it was the NCFS Longhouse, which you've heard us talk about a few times. So Sydney Opera House, obviously I did not do the engineering for this. This was Overup, did the engineering for it. And at the time, kind of just absolutely stunning, whether you like it or not. And at the time, there were a lot of people that did not like this project. It is truly a marvel, both in how they built it, installed it, and communicated how it needed to be built. So you can see here, kind of even the intent was derived from a method of complex geometry. You can see that that is really the form highlighted right there. So these are all extrapolated from old drawings that you can find on the internet. I was trying to illustrate that they had means of doing this, even, 50 years ago? 55 years ago. This was built mid-60s, right? Opera House was built mid-60s, I think. 67?
Just trying to think of when Peter Rice died and how old he was when he died.
Yeah, so early 70s, because
Yeah.
these drawings were dated from 73. For some reason I thought it was the 60s, but I think that was when the first drawings were released for it. So you can see here that they're using some of those methods of descriptive geometry that were outlined in that textbook in the 60s. I like this one because this one's really handy for structural drawings. And we do this a lot when we need to show structural information. What's happening here is this is all one member cut at 5-foot segments along its length. These are special segments. There was probably more happening beforehand, but literally they've drawn this section at 5-foot increments and said that vary it along that. So this is essentially what we did with our method of sections when we were talking about shear diagrams and bending diagrams. It's the same idea. We know that we could integrate between this point and this point. We could actually write a formula to calculate along those points. But we could actually do sections of it to illustrate what that point is. And that's what we did when we did our method of sections for shear and bending diagrams. So it's that same concept represented here. And you can see that, it varies along its length. I have done this on different, every time we actually cut a section around a building, this is essentially what we're doing. Often in a building, we're not varying that much around the building. You might have 20 sections along a building, where this has, 2, 4, 6, 8, 7, 15 sections just for one member to kind of show the variation along its length. Pompidou, with its Gerberettes, there's lots of interesting things to talk about this project, and we will probably talk about it when we talk about mechanical systems, I would imagine. What was really cool about this are the Gerberettes, these cast steel elements. I'm going to talk a little bit more about castings later on in the lecture. But this is very complex geometry. And how do you show how to make this object? How do you even tell someone how to do that? I've gone through the process, so I know exactly how to do it, and that was my workings with Cast Connects. But just to kind of give you an intent or an understanding of what they actually do, they start with a positive mold. So you take foam or wood or something that's a very easy medium to work in, and you curve it into the shape you need it to. Now we tend to work with CNC machines. Back then, they didn't have that sort of information. And just to give you a sense of the scale of these Gerberettes, that's a person standing in amongst the Gerberettes. So you would create a positive mold of it, and then you would take sand that you treat with a chemical that allows it to bind together, and you press it around the object. And you press it really, really, really tight, and then you break it apart along seam lines so that now you have a negative mold of your foam object, and you set it aside. And then you reassemble it with your sand that's been compressed and locked into place. So imagine almost like a really loose mortar, a mortar that if you poked at it, you could start to break it apart. You put it back together and you have pipes down into it that allow them to heat up molten steel and pour it down into the objects. If we have time, I'm going to give you a bonus mini lecture on the nodes. I might do a Cast Connects lecture just because it's so friggin' cool and they produced such incredible videos. They probably have even better ones. They definitely let me share some of their newest. I haven't worked for them for 8 years almost, or 6, 7 years. So I'm sure they have even cooler stuff now than the stuff I was talking about when I was working with them. So here is how they would have illustrated to a forge how they needed to create these Gerberettes. You can see here that they did a very similar thing to what they did for the Sydney Opera House, where they cut various sections along its length. So you can see this is section C. Section C can be found right here. Section D is right here. You can start to see those walls of the Gerberettes are starting to come together. This section B is right here through where in plan it actually has the opening. So this is elevation and plan shown relative to each other with multiple sections cut through it. So, this is using that plan view represented with elevation and sections cut through it at distances along its length. You've seen the 3D image of the Gerberette, and you're people who are used to looking at drawings at this point. So it starts to be a little bit easier for you to understand what we're trying to represent here. But if you hadn't seen the Gerberette, this would still be a little bit hard to kind of wrap your head around. Frei Otto, master of representing complex geometry, kind of software that did all of your stuff for you. Truly incredible work, often represented with scale models. The scale models were integral to his team building things in the field. They would literally build a large-scale model and transport it to site and do checks off of it to check what they were doing in the actual construction of the element. You can see here, and Dave talked about this last week when he was talking about, or 2 weeks ago when he did his fabric lecture, kind of really showing these complex forms. You can see here the descriptive geometry. These are the lines taking it and opening it up and showing it in different views what is happening with those objects. So they still needed to be able to draw it, because you could imagine that helps everyone understand what's going on. But he actually made really good work of topographic imagery as well, where they would take it and actually do a roof plan contour to give people a sense of the scale of the object as well as they were building it in real time. So there's the overall structure, or the overall kind of built work that needs to be represented, but it gets even more interesting with fabric objects for a few different reasons. Because when we're doing fabric and cable elements, we pre-stress things. So we need to know what length things need to be in the shop and what length they need to be in their final form. And we need to be able to tell people how much those things need to stretch, because we literally pull them into our shape. And you can imagine that the amount you can pull it, if you guys remember your stress and strain equations, that the amount you can pull it varies on force and the stiffness of the material. And Dave talked 2 weeks ago about warp and weft and how the material behaves differently in 2 different directions. You need to log in. Okay, so here's the new way to get in. Edsby doesn't work anymore. For whatever reason, we've been kicked out. So Malcolm, oh, come say hello to everyone.
Hi.
Okay. So we're going to go in here now. So if we go into our normal stuff where all the assignments and things are, up here, information, there's actually the video meeting link as well. So that is a different problem. We are one of the people that is kicked out today.
Okay.
We're normally one of the first people on, so it doesn't tend to happen to us.
Oh.
But a lot of the other moms and dads, mostly, have been saying that it's bonkers. Like, this module, about 50% of the class can get on. So it's been a real struggle. So you're freewheeling it today. You can watch the videos that are posted in that on the TV if you want. You can find them on YouTube, or you can throw it, or you can just watch them on that, whatever works. Okay, buddy. Oh, I love the hugs. But I have to tell everyone all about complex geometry, representation of complex geometry. So we have to be able to tell people how much this stretches. And you can imagine the kind of integration that happens in that, how much we have to check and recheck. It is not a, determinate problem. It is an indeterminate problem where we have to make some assumptions, check things, compare those results, and then start to hone in on our answer. So this is a horrible graphic. I keep meaning to get a better version of it, but someone hasn't given it to me. But this is all of the fabric pieces for the sea lion sound at St. Louis Zoo. This is literally, they would roll the fabric out on the ground and cut it into these shapes. But eventually, we need it to make this very kind of contoured shape. So there are a few things that happen here. These lines are our work points. So that's where we need elements to be. The green line is the cut line, and the red line is the weld line. What's not shown in this is that this is just a little bit too small for where we need it to be. Right, Dave?
Yep.
It's a little bit too small. And then as they're erecting it, they actually pull it into the final position it needs to be. And that is
like stretchy pants.
Like stretchy pants. Thank God for stretchy pants. I don't know how I would have lived. Oh, I live in leggings now that I don't have to go anywhere. So they stretch these out into their final shape. And it has to be very precise. Like, there are real calculations that go into this being able to stretch millimeters. How much would you have suggested one of these panels stretch?
Roughly 1%. So on a 9-meter panel at 90 millimeters.
That's a lot. That's almost 4 inches that we're talking about stretching that panel of fabric. But you can see here that it helps to kind of give this graphical image to the installer that corresponds with kind of all of these. Now this is a jumble. Each one of these would have actually had a page that looked like this, that then corresponded to this isometric view to give intent, to help somebody understand just what the heck is happening here. Okay, this is my project that Blackwell was actually hired to do, but nobody kind of had the means or the time to do it. I'm sure a ton of people at Blackwell would have figured this out. There are a heck of a bunch of smart people at that firm, but it was just as I was founding FatLab. And the team at ZAS knew me, both through Blackwell and through my work at Cast Connects. So they said, Shannon, can you help us out here? We want to engage Blackwell and or FatLab to do this work because we can't get the solutions we need. Now, Arup was the engineer for the base building. Again, smart engineers. But they were kind of overwhelmed at the time, not because they couldn't have figured it out. I'm sure they could have come up with a reasonable solution, but they didn't have the time or the fee to do it because that wasn't part of their scope, and they were being asked to do something well beyond their scope. They also didn't have the manpower to do it, so they said, here, you can do it this way. It works. It's not going to give you the dreamy vision you're looking for. You could hire us as another separate team to do this work or hire someone else. And so ZAS said, listen, let's keep the scope separate and we'll go out and ask someone else to do it. So the original conceptual vision for this was a cloud. That was what they wanted to do. But obviously it's impossible to build a cloud, and it might have been a little bit too literal as a cloud. So they wanted essentially a pixelated cloud. They knew right away that they were going to have to get into some kind of interesting process to solve this and to make it feasible and reasonable on a budget. So they hired a mathematician. This was actually done by Mesh Consulting. Fantastic guy that heads up that firm. I've worked with him on and off for various projects. I met him completely independently because his sister and I played hockey together for years. But he is a mathematician that works with and for engineers and architects. He has his own firm now doing absolutely insanely amazing stuff. He'll also do programming and write scripts for things, but just kind of way too smart for me to understand most of what he's doing. Really fun, cool person as well. So his goal was to take the boundaries that the architect had laid out and create an image that would appear randomized, but make it as standardized as possible, which are two absolutely conflicting things to do. So the goal was to create standardized triangular elements. There were actually only 3 different triangles that were then combined into 4 different patterns. And then those patterns could actually be created. We didn't know which way the fabricator would want to create this, if they would want to make objects and bring them to site, or make strips and bring them to site. So this was before we were actually brought on to the process. So some of the thought process was trying to build in multiple ways that this could possibly be fabricated. You start with a broad problem and you start to find solutions and narrow down. Sometimes you find more problems that you didn't even know you had, and then your context starts to become narrow and narrow until you get to the final solution. So they were trying to solve a few problems here. One of the things that's very interesting is this image here. You would think a rolled out image would be kind of easy to produce, but it was surprisingly difficult to get that information from anyone because everyone was working in 3D imagery. The mathematician, the architect was working in Revit, and I was brought on and needed to be able to come up with an engineered solution. And I'll talk about that in just a minute. And first thing I said was, can I have a rolled out elevation of this building? And no one could make it. So they actually hired the mathematician, Daniel from Mesh, to create that for me. It took them like 2 days work to actually produce a rolled out image. And again, you would think Revit can do elevations, but this was a bit more complex than your standard information. We were talking about something happening in 2013, kind of, 7 iterations of Revit ago. So what was so complex about this? Well, we had all of those triangles, so that adds some complexity as well. But what's not apparent from this image, because it's a 2D representation, is actually all of these triangles are faceted relative to each other. So it's not just a flat plane wrapped around it. Every single triangle is at a different plane along that curvature. Also, that curvature was actually 8 different radii. you can see the segments of radii here. So this had the same curved radius. This was a separate curved radius. And we would go down along, we had 8 separate curved radii. On those separate 8 curved radii, we had different facets. So we had to support this faceted surface off of our concrete structure. So here's our concrete structure back here. So varying curved planes of the surface element, faceted windows that were offset from our structure. Now, it was approximately 450 millimeters offset, which is a long distance. 450 millimeters is a far distance to have your surface relative to your edge. But you know that we live in a world with more insulation requirements to meet higher and higher R values. So you need a big exact gap there to kind of fit everything in. So we had a surface that was very much offset from our structure. But even that 450 millimeters wasn't consistent. As we varied around those 8 curves, the facade had a slightly different offset for each radii, plus we were dealing with the faceted element. So you can see that where it's offset here and where it's offset here are already 2 different planes. So trying to offset a sloped surface from a curved plane, how do you measure absolutely anything? The biggest difficulty here was a compressed timeline. In a normal world, you would build the concrete building, the concrete guys would leave the site, the steel guys that are doing the facade or the envelope, so the light frame steel guys, would come in, measure the concrete, build a model of its exact as-built condition, and then they would make their steel. They would come to site, they would install their steel, they'd leave, and then the window team would come to site, measure the exact window openings that they had, go back to their shop, build the windows, and then come back and install them. So 3 separate construction elements happening. We were on an insanely compressed timeline. While I was doing the work, the concrete was already being cast. What they ultimately wanted was that the second concrete finished, they wanted the facade being installed, and the second they had the first window opening up, they wanted the windows being installed. So they even wanted the top floors of concrete not being finished before they started the lower floors of facade and windows. So, you know, what would normally be like over a year construction, they wanted to be happening in 3 months. 3 months of construction. So this is where Dave and I both always talk about understand precedent, refine as appropriate, and then only innovate when those things don't work. If you have a workable, usable solution, it's probably because it is the cheapest usable, workable solution. And so you wouldn't go reinvent the wheel to only come back to use the wheel. So that's where we started. We said, let's look at precedent. Precedent would be, you go in, you put in your studs. So this is talking about not wood studs, but light gauge steel studs. Between your floors, you could follow the outline exactly that you needed, and you just frame around your window openings, and then you could put your window in. The problem with that, like I said, is that we had a 450 millimeter offset, approximately, and our windows were very heavy. So these are kind of cantilevered out from the building. So they actually needed structural support in a way that all windows need structural support, but it's usually pretty easy to just kind of put your steel in and hang your window off of it. This needed some real thought to get that structure out to pick up each one of these windows. So then we said, well, you could build in a little more tolerance with a 2-way stud system. And you have a series of studs this way and a series of studs this way. If they're each 200 or 225 millimeters in depth, well, you're now out approximately to your window spot, and now maybe you can just frame around your windows. That left them with a timeline problem and a precision problem, that they were worried that they wouldn't know exactly where their windows were going to be. It left a lot in the hands of the stud installer on site, which might not have had the precision, because that's outside of a stud installer's scope. Not to say they can't do wonderful, amazing things, but this might have been outside of their scope, and they wouldn't have found the problem until it was too late on site. So we said, all right, stick with your basic, simple method where you don't have windows. No problem. We'll build steel frames everywhere you have a window, and they are locally, structurally designed, and those can just get installed and the windows can be put in. The problem with this was that we needed moment connections top and bottom. Anything in the field that's a moment connection is a pain in the butt. Switching from concrete to steel is always a pain. We either needed things cast in to accept these, and I've told you before that things cast in are always the thing that are wrong. Like 60% of the time, they're out of place. So this didn't give us a lot of tolerance, and these were somewhat difficult elements. And you can see there was only 2 ports of support, so it needed to be held in place until these complex connections could happen. So we said, well, what if we did the same thing, but we made 4 supports, so it could be just pinned connections now. We would resolve all of those 3 degrees of freedom. I mean, we know it's actually 6 degrees of freedom, but we would be able to prove that we had equilibrium in the y direction, the x direction, and spinning about z. That we could do 4 pinned connections now instead. So a lot easier to detail, a lot easier to install, especially quickly on site. It still left a lot of stud work, and then there was infill stud work here. They still needed to solve the problem that their studs in the other zones had to come out to pick out the facade. So they still found that they were left worried about precision on this. They said, you know what, we like these ideas, but we still think that we're going to find problems when we install this on site. And we said, yeah, there's definitely a risk that, this steel will be perfect, but everything around it might not be as perfect. And they said, listen, we want to make this as standardized as possible. We want people building this in the shop where they can do it to laser precision and then bring it to the site. We said, all right, we have an idea. Let's make a series of frames that can be perfect. The window openings in them can be perfect. And then not even that, you can actually weld the studs into it, so you actually just bring a series of basically steel frame panels that you pop in around the building. These would have pinned connections to the concrete that would allow for tolerance, so that if those cast-in elements were not perfectly where they needed to be, they could have adjustment to our steel panel. So the steel panel wasn't dependent on those cast-in elements being absolutely perfect. So I said that we had a lot of issues still trying to resolve that. So we had a curved concrete edge. Problem number 1. Like I said, it wasn't even one curve, it was 8 different curves. Our track that we needed to put our studs in had to be set back from the edge of the concrete. We then needed to make sure that there was tolerance for the stud. You always need tolerance built in. If that is our track zone, or where they would allow our track to be, we actually wanted our track to have a bit of tolerance in there. But then our steel frames aren't actually going to be built in curved elements. We're not going to roll steel, but we want to build it in a series of straight line segments that our stud could go in following that curved line. So our stud could follow that outside line, but be connected to this steel frame that's in that straight line element. We had another added challenge, and I kind of alluded to this, where we said that the windows are actually the whole facade was 450 millimeters outside, plus minus, from the edge of the concrete. The facade is pretty light, and we ended up having them do like our single stud, and then they built it up with 2 layers of light gauge kind of steel grid to pick up the main facade. Our problem is the windows, where we had nothing that could stack out in these open zones. We needed something that could frame the windows and be absolutely perfect. So we said, it was you that called them socks, and it drives me nuts. It was months of referring to these window socks, because we needed something to differentiate from the steel panels.
Architects like things with names. They have to name everything.
So we came up with these steel window socks that would frame the window perfectly, so the full perimeter of the window. Our problem was, in our standardization of our frames, we tried to come up with a method that cut through windows the least amount. But you can see sometimes here we would end up with a frame where a window actually crossed 2 different steel panels. I tried to do my best to limit that. What you can't see here is that this is a line right here. You're just leaving?
Yep,
Yeah.
see ya.
All right. You can see here that is actually a crank in the frame. So this was a straight line segment, and that was a straight line segment. So every panel actually had 2 segments built into it to help follow that curve. These are the cutout window socks that they ended up using. What is not clear is that they are different lengths. They are different shapes. And I'll talk about that in a minute. So we had 2 different things we needed to do. They needed to know if this was even feasible to build. They didn't want it to cost a fortune. As much as they were willing to do something innovative, and we had a client who was willing to do something innovative, they needed to prove that it followed kind of standard procurement, or as much as possible standard procurement methods. They went through the process and found that they couldn't get anyone to design what they needed, so they were willing to hire Black Lab, or that was what I originally wanted to call my company, but somebody else already had the name, an architecture firm in Toronto, oddly enough, that opened a few months after I did, but they had already locked down the web address. So I was mystified who owned it for a while, but Blackwell and Fat Lab, they were willing to hire us in partnership for a, not for the full process, but for a feasibility procurement, just cut and ripped my chair, a feasibility, basically design set. So we needed to be able to produce a flat surface drawing in 2D that was the rolled out elevation that said the number of panels that would be installed, the total weight of all the panels. I actually gave a max panel weight and an average panel weight just so that they could see. They needed the max panel weight so that they could figure out what crane they needed, but they might not have needed that maximum capability for all the panels, so that they could also do a tonnage takeoff. And then I gave a typical panel for each type as we went around the building for the 8 different radii. And I needed that all to be in a 2D producible that they could go out to different fabricators and say, can you build this? So this is what that original producible looked like. So here is that rolled out elevation that mesh gave me. And the grade zone is the the panels that we're talking about. These zones here were actually something else. They were slightly different than the context of these types of panels. And then this kind of more highlighted panel is this panel right here, where it shows exactly what we were imagining. You know, an HSS steel frame box with the windows and steel studs in between it. There's a cross section right here showing what we expect that to look like. Here is the edge drawing showing the intent of how the track needs to fit relative to the concrete slab. And I actually modeled this in 2D as well. Once I had the rolled out kind of scope worked out, this was somewhat easy to kind of go back and forth. I had, I drew all of this in elevation, and I drew in plan in 2D the edge of the concrete to show kind of how I could fit my track and actually make all of these straight line segments hit within it or not exceed that. I showed intent for how we could build in tolerance. So these were the details. These would be the cast-in panels and how tolerance would be built into it. So these HSS frames would slip in, shimmed tight, and then tack welded. So they could have the crane and a person inside get them in place. They'd wobble around a little bit, but they'd be stable until they shimmed it and tack welded in place. But that doesn't require your most expensive welder either. So it was taking all of the phases into consideration. I listed criteria for AESS for the panels, for some small spots that might have been visible. And then I gave so here you can see the panels varied in 4.2 meters to 7 meters in length. They have cranks, the height of the panels. These were all, they also needed to be kind of trucked to site. So they had to fit on the back of a flatbed. So that was a big criteria within it. So, you know, the top of a panel compared to the bottom of a panel needed to fit on the back of a flatbed, which is about 3.6 meters. So here I say that the prefab steel frames will weigh between a min and a max, and I had a chart that gave that information. And I said that the standard frames represent the majority of the cloud surface, or actually 76% of the cloud surface. So the standardized ones are the majority of it, and there's a few that don't fall into that criteria. So I gave them all the information they needed to build the project, and they came back with a fabricator that was willing to do it. The big thing that was the feedback from all the fabricators was, that's great, our biggest thing is going to be that we have to build these models and kind of get going on it, and it's going to take like a month for you to hire us and get the process going. So that was the preliminary feedback. And they said, that's a big risk, so we're going to make ourselves very expensive. So the client came back and said, this is going to be a problem. We don't want it to be this expensive. It's going to be a problem to be this expensive. So Dave and I said, well, we could do the 3D modeling aspect and essentially produce what is almost shop drawings. And once they're hired, we can send them 3D files that they can build from. He said, we'll take the risk of generating the 3D geometry, and they just have to build it. The pricing came back much, much, much lower because we were willing to take the risk. But it's not as big of a risk to us because we have access to the information in a way they don't. So we found a steel fabricator that was willing to work in this new format where they would actually get 3D fabrication drawings from the not base building engineer, but the facade engineer. and actually build directly from that. Could they have built from the 2D drawings? Yes, they could have. I gave them all the information they possibly needed. The architect was able to generate an Excel diagram that said what this point right here was at every window panel edge. So our faceted windows at all of those corners, so there could have been 3 to however many, 10 per window, could have a representation in X, Y, and Z. That could be given to them. They could input that into whatever model they wanted. And I said, based on that node right there, your window sock needs to be 65 millimeters away from the surface, 19 millimeters away from the edge, plus minus 19 millimeters. We gave them an incredibly tight tolerance. We said that the steel frames need to be less than 6.4 millimeters away from the stud track perimeter, so that the stud had play to be built into, and that stud track had to be 25 millimeters back from the edge of the concrete surface. So all of the information here was here to build it, and we had a data set of all of those points, and that's it. They could have built it. No one was willing to take the risk, so we said, we will actually generate these for you. And they said, okay, here's our price, and everybody was engaged to go to it. So here's where I redefined the process. I said we would create a geometric resolution drawing package. Dave and I started throwing this word around, and we did it on 3 or 4 projects. We've since been in a meeting where somebody said, do you think it would be possible to produce a geometric resolution drawing package? So we've started to hear our terminology come back to us, which is really fun and exciting. Maybe someone else was using it at the same time, but we hadn't heard anyone kind of get that verbiage out there. And we did 3 or 4 projects in the city of Toronto. So, the word is kind of out there that this is what we call it now. And so this is where I would produce 3D models used for construction. The very first thing I needed to do was produce a 3D image in my software of the concrete building. The base building engineer, I didn't have access to the Revit drawings. First off, they were unwieldy, and they weren't easy to work with. I took the engineer's 2D drawings and produced this drawing right here. I produced in the software I was using, which was SolidWorks, a 3D representation of the concrete structure. So I was able to generate this 3D image based on 2D information. I then took the data cloud from Mesh and ZAS and produced this image. So each one of these little dots around the window is this point right here. So that's that cloud of windows around the perimeter where each of those little dots could be conveyed in an Excel file if you wanted it as an X, Y, and Z coordinate. So there it is close up. There's the outline of the window. You can imagine that so these are all around 0.5 meter away from this concrete edge of the building. And you can imagine that what I need to produce needs to be 65 millimeters back from that and 19 millimeters wider than that. So I need something out around the outside, but also 65 millimeters pulled back from that. So the very first thing I did was create the steel panel surface. So this is where my steel would fit in the track. So this is literally me taking the 2D plan that I had generated in CAD that showed where the HSS frames would go, and I converted it into a flat surface relative to my concrete building edges. So there is my flat surface. And I said, all right, I'm going to project back an image of my window on that surface, but I'm going to make it 19 millimeters wider. So no problem there. And then I framed my opening. We also needed 150 millimeters from the concrete edges, from above and below. That's to give us, our ability to slip it into those tabs that I showed you in the construction element, but also to have it fit on the truck. So we kind of built that element within the truck, and we needed 50 millimeters in between our panels to build in tolerance. So then I was able to extrude those same window elements out. I still had the problem that I need those to be 65 millimeters back, but I need my planes to be flat relative to each other. So all of these planes are different from each other. It's not just a straight extrusion out. So here's where I came out 150 millimeters from my steel surface, and I came back 65 millimeters from my window surface. And then I started adding my sock plates, or those steel elements around it. So I would create surfaces on all of those, and then I needed to cut those back to project onto, to meet up with the steel frames. So here I put in my HSS's that would allow these sock panels to be welded. So these needed to be flush to each other, but also align with the element of the window edge, which sounds so much more simple when I tell you about it, but the kind of analytics within this was insanely complicated. And then the rest was mostly just prettying it up. You can see all of the dimensions that were relevant here. Then I needed to kind of cope everything and show them where everything would need to be welded up. So this is one completed steel panel. There is that panel right here. I had a contract of 6 weeks to produce the 3D files for all of these. The first panel took me 3 weeks to resolve. And I'm not talking like 3 weeks because I rolled out of bed at 10 in the morning and cut it quits at 3 o'clock in the afternoon. I'm talking up all night, pulling my hair out, trying to make this work. Because all of the problems kept appearing. How do we deal with a window that cuts across 2 panels? All of this 19 millimeters, 65 millimeters offset, how do we get it flush to the surface of the HSS so we can weld it, but not taper in so that we don't meet that 19 millimeters and 65 millimeters. So I had 172 frames, and the first panel took me 3 weeks. I was, in a panic, as you can imagine. The second frame took me 2 days. So I was feeling a little bit better. The third frame took me 3 hours. So then I was starting to be able to knock out several panels a day. So you can see there are all the level 2 and level 3 frames. It got a little more complicated again when we had those zones that weren't part of the standard frame panels. So this here is where we're kind of underneath the concrete, and we actually tapered up for door openings. So this didn't fit in between 2 concrete floors. We actually had to cantilever these ones down with outriggers to kind of pick up the kind of overturning force. Then I did the level 3 to 4, then I did the level 4 to 5, and then they realized that they didn't like the way they were detailing their parapet. It kind of went out of the bounds of the standard parapet that they were willing to kind of warranty. So they asked me, would you do the parapet conditions as well? So I said, sure. And for those we actually did, because there was the ability to hide things a little bit more, and there was no windows in it, we were willing to weld, and the loads weren't that high, weld these down to cast-in tabs that we moment connected to, but we had a lot of tolerance because they just made the cast-in tabs bigger than we needed. So literally, I sent the 3D files for every single one of these to the fabricator. I actually broke it into frames and window socks. The window socks, they actually took and laser cut based on my model files. So that was a whole other process, was actually producing the frame files and then the individual sock panel files so that they could cut each one to exactly the size and dimension they needed. Because you can see if there were 172 panels, each one might have 10 to 15 kind of window sock panels within it. So I needed to produce the step files for that. But they did. They literally laser cut from my files. So then the question became, how do we know that they're building them right? Like, how do we actually guarantee that this is happening? Because, like I said, I was sending these both to the steel fabricator and the window supplier. So the window supplier was making their windows at the same time that the concrete guy or the steel guys were making their frames, but the concrete wasn't even cast yet. It was starting to be cast as we did it. So by the time I was wrapping up, they were pouring level 3 or 4, I believe. And by the time they were pouring the roof, they were already installing steel on the lower floors. So how do we review it? Well, it's impossible to say this should be the dimension, because how do you guarantee that? Like, it's you have no context to it. And in X, Y, and Z kind of in a 2D plane, you can assume everything's at a right angle and your measurement should be right. As soon as you get skewed angles, you need multiple measurements. So what I determined was that I would pick 3 measurements from the same point, and if in 3D. And so what it needed to be was that a tape measure could touch this point here and pull and measure to that point there. And if we were in 6.4 millimeters of tolerance for all 3 points, we would have met the intent of the 3D model. So I actually produced, so this was a whole separate contract after that, where they actually hired me to do quality control, where for each panel, we did 2 checks per panel, so 3 measurements from 2 points, so 6 measurements per panel, to verify that they were fabricated as intended. So here's just a picture from Dieter Jansen, who was working with ZAS at the time. Fantastic photographer as well, so he gave me the rights to use a lot of his beautiful photos. Here is a piece of the steel on the ground, and here are kind of blown up versions of my drawings where they've actually added more information to help allow themselves to do internal checks as well, which is wonderful. But the owner wanted to know by an independent source that they were actually being built to tolerance, because there was too much at stake. They would much rather fix the problem in the shop rather than after it was already installed in the field. So here is me actually measuring the points in the field. They were producing these so fast that they already had them loaded up onto flatbeds, and I would have to climb up on the back of the flatbeds to do the measurements sometimes. That's me up here, and that's part of the architecture team. Came out. Most of the time I was keeping up with it, but they had a huge rush where they actually produced a ton of the panels all at once, and I needed help to do some of the measurements. Some more kind of just beautiful images. It's funny when you're working with these things and you look at that model, you imagine them just being these little tiny steel frames. This was one frame. Here's where they drop down around a drop panel in the concrete. But these are the size of the steel frames. This was the guy who ran Norak Steel. They thought this was a super fun project, and they were willing to take a chance on it, which was incredible. You just get a sense of the size of these. So there are 172 of these enclosing the building. So there was one other thing, and I've alluded to it, is that we needed installation tolerance. So we needed them to be able to install it and then adjust it around a little bit to get it perfect. And we needed it in all degrees of movement. So X, Y, and Z movement plus X, Y, and Z rotation. We had this option built into it with every third or fourth panel having a turnbuckle that allowed it to move back and forth. We could hand tighten things up here. We found that a bit too bulky. So this is where we came up with this one. And I showed you this already, but here's a close-up detail of it. They could literally slot these in, and these were discrete elements. So they could move these up and down. That was slotted in this direction, so they had some play. And then those got welded inside here. And then these shims would be put in and welded in place after it was adjusted tight. So it gave them play in all directions. I know I've already told you guys this story, but you're going to hear it again because it's just such a great story. They called with a site problem. They said, massive problem, these things don't line up and the windows aren't going to go in right. You got to solve the problem. Come to site immediately. And I was like, well, I'm flying out on a plane in like 3 hours. Can this wait until I get back next week? And they're like, no, this is urgent. All hands on deck, get to the site. So I was like, all right, I'll be there in 40 minutes. So got to the site, and the issue was at this point right here. And they said that it wasn't aligned, it wasn't flat, it wasn't flush, and the window was going to have a problem. And when you looked at it, it did look like that. It did look like a funny problem to have. When I got there, though, and I looked at the problem, right away it was obvious to me that what's not apparent when you're working on the project is that this is going to have drywall put around it. They're going to hide that steel, and there's going to be some shims, wood shims with plywood or with a drywall. So there was the ability to not have this be exactly flush. It needed to be flush with the HSS to weld. And it needed to have these lines here be absolutely perfectly 19 millimeters wider than the window and 65 millimeters back. That edge there was the be-all and the end-all of these window socks. What happened back here, it just needed to be welded to the HSS. You can see it really well in this image here. You can see you're looking straight on at the edge of the panel, but because this is where a facet line happens, and this needs to be flush with this HSS, and this needs to be flush with this HSS, you can see that it looks like that steel slopes in. You can see this is the point. You can see that those two things are on different planes from each other. And that was okay. All that mattered was that this face edge of that steel panel be a perfectly flush line. This one's a really good one. You can see it right here. That you would look at this on site and be like, oh my God, we have a problem. But this line here and this line here needed to be perfectly aligned to each other. So if you put a string and glued it here and a string and glued it here, it should be perfectly flat against the face of those two panels. So we took a ruler, not even a measuring tape, but an actual ruler, and held it up. Again, we reached through and held it up flat against that surface, and everybody's anxiety went way down. And I said, I'm so glad we were able to solve this problem, but Dave and I are heading to get married right now. Our flight leaves in an hour and a half. We got to hightail it from the site. My wedding dress is in the car. Got to go. And so we headed off to get married. I didn't get a single call from site after that. Every single panel went up perfectly and smoothly. Windows went in perfectly. No drywall issues, no major surface finish problems. Tolerances were fantastic. So all in all, an absolute incredible success, I think. And here are just some kind of stunning pictures of it happening. There's the weird problem right there, the one that appeared to be a weird problem. You can see we had drop panels that we needed to notch around. kind of different. There's the element where we didn't actually have a concrete bottom we could connect to, so we had to cantilever down. Here you can see where they're still installing steel on the other side, but over here they've actually installed windows and started putting their facade on. I love this image of it. And then here are some interior images of the final product. You can really get a sense of the depth, like that the concrete edge is somewhere here and the windows are way out here. These are mullions within the window system themselves. So I gave all of that data. The window people in the end would have asked for that same data point information I asked from Mesh. So we already had it ready when they needed it and were able to send it to them. So truly a unique project. So how do we convey actual information? So, this is where we kind of rethink the standard construction document package. That doesn't mean we need to rethink the contract document package or the tender package, but the construction package may need to be rethought. We already see this on highly complex projects. Specialty sub-consultants receive 3D files all the time, and specialty product suppliers will send you 3D drawings of their product. So I know Cast Connects has some off-the-shelf products. They will send you 3D CAD or a step file that you can actually import into your Revit file to use to represent their product. So this isn't an unusual process. Where it's unusual is using it as our construction package. Normally still we need to go through a very complex manner to represent everything in 2D, and then what everyone really wants is the 3D file anyway. I'll show you a few more projects. So this is Integral House that Blackwell did with Shim Sutcliffe. This was kind of just when I was starting out at Blackwell. I did some review on it. The really cool thing about it is the curved windows. So there's actually curved windows on this project. And we had an interesting thing that everybody needed to talk about this line right here. Obviously, our grids go like this and this, so X, Y. You can have diagonal grids if you need to, but we spent a lot of time talking about this surface line here. How far are the windows from that surface line? Exactly like I talked about with the Lassonde project or the ZAS project. So Dave said, well, let's have a new grid line. Let's make this curved grid line called our integral grid line, and start talking about it that way. Now, if it's not clear, he, before his passing, the owner of this house, wrote all of the calculus books that the majority of universities use. So I have spent hundreds of dollars on his books throughout my lifetime for school. And he was also a lover of the arts, so he wanted a beautiful house that was actually used and showcased for a lot of kind of concert performances, a lot of events. In fact, if anyone is a Star Trek nerd, like myself, Star Trek Discovery, the home that the main character grew up in with Spock, they actually used the Integral House to film in. So go back, watch that. You'll see images that look very much like this. Truly a stunning building. I've had the opportunity to go to parties in it, and it's just truly astounding. In fact, this is a picture I took. It photographs so well that my mediocre photography skills can take this image to show this project. Dave and I talked about this project in the last video, where we talked about the reciprocal frames for the longhouse, where we, kind of back before anyone was doing it, we didn't even expect it to happen. We produced a 3D CAD drawing and sent it to the architect, who just sent it off to the fabricator, who actually milled the wood from that file. Different story, because it's a smaller project, obviously, and we weren't bound by a lot of the same constraints that you would be, typically. Again, Dave has touched on this with his fabric and tensile structures lecture, but how to convey 3D information was and is an ongoing conversation for this project. You need to be able to verify it and check it and communicate it, especially when you're talking about a project that is supposed to move and have large-scale deformations during construction. The whole idea of pre-stressed tensile structures, the cables need to stretch to be tight enough. So you cut them to a certain length and then stretch them to purposely have large-scale deformations. So how do you verify those 3D points in the world? And so that has been kind of a massive difficult. That's probably one of the math is the relatively easy part for that in this project. One of the ways they handled it was to send a 2D diagram, an unrolled elevation for some of the objects, showing different grid lines. Oh, I didn't include it. The best part is they actually sent a list of geometric node points. So they actually sent files with X, Y, and Z coordinates for all of these points to be able to say to the contractor, this is where they are, this is where they need to be. It was way more complex than that. But part of the way they communicated how they got things there. Now, as you tighten things, you're going around the project, so there's sequential elements to it. It's a much more complex entity than what I just described. You need lunch for them, don't you? Yeah. Is that okay? Yeah. All right, thank you. So this one I just wanted to show you. I have a few others just I want to touch on. I didn't want to make this a full 3-hour lecture, but I wanted to give you guys something interesting to kind of take away from this. This is the Rosalie Sharp Pavilion as part of OCAD, kind of just down the street from the AGO, so lending itself to that same kind of swoopy facade element. They needed to be able to convey complex geometry in a 2D element form. You can see here that they've shown an elevation, they've shown a top plan, side elevations, and then isometric views, both bird's eye and worm's eye, to help show intent. And here's one where they showed some points as straight line segments, and here is the 3D coordinate points for every single node on this facade. So an X, Y, and Z for every single node. And then here, they've taken a step further where they've shown erection intent. So these are the elements that would be cut, they'd be welded together, and then these segments would be brought to site as segments and connected together in place. So this wasn't my project, but I was able to overhear a lot of kind of the conversations around it. So kind of really feeding on what we did for the Lausanne project. So this was about 2 years after that. Queen Richmond Center, so this is 134 Peter. This is, you've heard me talk about it a few times now. This is an 11-story concrete building perched over a 4-story existing heritage building. The mandate was that it needed to be, the facade of this building needed to be able to be viewed from as many vantage points as possible. So this needed to be a glassy atrium that you could view this structure, and minimal work could be done to this facade. It wasn't strong enough to use as a lateral system without overloading it, so we needed to be able to, or they needed to be able to punch and go through it to get the loads down to the ground. Steel fabricators were a fantastic fabricator, and the architect was working with Stevenson Engineering on this project. They brought in cast connects to help deal with the lateral system because Sweeney and Co., which were and Co. at the time, wanted to do something called delta frames as their lateral system, so gravity and lateral system combined. I've given entire talks on this project, like 2-hour talks on this project, so I have lots of interesting, amazing slides that I'm not going to get to show in this unless I squeeze in a Cast Connects lecture at some point, just because it's so fun and cool. But Carlos and Michael showed up at the meeting and said, all right, we have some ideas of what we could do for you. They modeled a few options and actually came up with some 3D printed elements. The real complexity was that these steel columns needed to be filled with concrete for both strength and fire protection. But how do you pump concrete into this object? And concrete cures, so there's shrinkage. They were able to deal with that at the top by some smart detailing, but how do you deal with that 2 more times here? So it needed to be hollow to allow concrete to be pumped from the bottom and pressurized up to the top. So these needed to be openings here. So Cast Connect said, well, we could do something like this, and then we can structurally engineer this to be able to transfer your gravity loads and your lateral loads. Like I said, I have about a gazillion slides on this. This one might be one of my absolute favorites. After they cast it using the same method, the sand cast method that I showed you with the Pompidou Gerberettes, where they would create a foam or wood positive, and then a negative with sand, and then they fill it with molten steel. After they do that and they knock off all the bits, just to help it kind of ensure that the stresses are equalized, they'll reheat it and control the cooling process. Because when it's in the sand cast, they control how it cools, but if it cools too fast, it would crack. So they can do that to like 95% accuracy in the sand cast mold, but sometimes what they'll do is heat temper it again, where they'll heat it back up and allow it to cool in a very controlled way. So this is this massive thing. It looks like it's a teeny little thing in the oven just being heated up, but here's a sense of exactly how large they are. These are them being installed. I have time-lapse videos of these being installed. I have 3D animations of the liquid being poured into it. I have into the sand cast. I have 3D animations of the cooling of it. I'm gonna find a way to share all those with you, just because it's too cool not to. So with 3D geometric resolution, why do contractors charge so much? Well, 1 is risk, and 2 is timeline. Geometric resolution being taken on by the design team cuts down on risk and timeline to the contractor. But that risk gets transferred onto our team. So our fees need to go up accordingly because we are providing an extra service. And it's not always apparent to the owner that that is the case. We see this more and more in kind of the producing of drawings all the time, where after we've gone through the process of creating our 3D models, the project goes out to tender and the contractor says, okay, I want your drawings, I want your 3D drawings. But they were ours for our intent, and they're supposed to build their own based on all the 2D documentation they've been provided. So if we're taking the risk of them using our 3D models, that cost transference has to happen. The industry as a whole needs to understand that we are, as the design team, taking on that risk. So you can see here that a bidder doesn't have any control. They don't have control over what's happening. We have more control over what's happening. So they're bidding on a lot of risk. So high risk, high cost. Geometric resolution limits the risk and lowers the cost all around, so transferring the amount of risk and cost that is there to our team should be totally reasonable. The overall product is still a lot cheaper. Same thing with timeline. Time on site means a high cost. Geometric resolution limits the site work, which lowers the cost. Do we eliminate 2D drawings? Not a chance. We still need those. The concept gets shown that way with renderings and context, scope, division of scope, so specifications and general notes. Highly important that that gets conveyed in 2D because that's the readable. That's the you are bearing this risk, I am bearing this risk. You must build everything this way to this tolerance. Kind of the outline of how things get built goes in that scope. Means and methods. What are the materials being used? What's the procedure for making them? What kind of finishes do we need? That all needs to be in a 2D element. And tender. A lot of this geometric resolution can be happening before tender, but would also continue to happen after tender. But you need to be able to go out with something to bid, and that's where having a 2D drawing could really help. So like you saw with the Bergeron Center for the Bergeron Center for Excellence, which was the engineering building at York University, could have some 2D inaccuracies because the entire scope was there for cost. Anything else was just about final placement. So those 3D geometric resolution drawings didn't change the cost at all. It just told people exactly where it needed to be. So we were able to shift some of that timeline for the producible to after tender. So how would Baby Bowick's Jungle Gym drawing set look different? Well, we would still have, instead of DD, tender, and construction, having a slew of 2D drawings, we would limit it to just a few 2D drawings, but then in construction, we would add 3D models for construction. But the design team gets paid. So in this, I was the designer and I was the mama of the Jungle Gym, so I deserved to get paid for bearing that risk. You know, we cut out hundreds of thousands of dollars of the cost for that. My fee to do that was not hundreds of thousands of dollars. It was not even, it was a fraction of hundreds of thousands of dollars. So to transfer that cost difference, some small amount of that cost difference onto the people that are generating it is a reasonable and responsible thing to do. So everybody wants to talk about integrated project delivery, but it has no real definition. You know, we have all kinds of different project deliverable types now. The standard was, you know, your standard procurement method where we went out for tender, people bid on it, which would be your bid package. But we have design, bid, build, P3 and IO. P3 and IO were all the rage kind of in the late 2000s, early 2010s. The reason why is that all of the costs were saved, or the low costs were thrown into the early projects. All of those people that were kind of taking projects so far could afford to do it on the first few projects, but eventually the costs got added into future projects because that cost can't be a total savings all the time. It has to go somewhere, unless you're actually cutting down on timeline and construction, which it wasn't. And instead what you had was multiple teams producing drawing sets. So the cost actually in the end was bigger. And we're seeing that play out now. I'm sure there are people that love that format, and institutions still love it, but we're starting to see it fall out of favor a little bit. But the whole concept of integrated project delivery changes depending on who you're talking to, where you live, and what type of project it is. But essentially it means BIM and giving someone your BIM model or your integrated model. So then the thing is, can we actually even build this cool stuff that we're designing? 30 years ago, it was hard. It's getting easier and easier. You know, like I mentioned roughly earlier about 3D printers. You know, when I started doing this, people would say, can you 3D print structural elements? And the answer was no, you couldn't. There are printers that can do structural grade 3D printing now for small elements, not large scale elements. And having been through the process with castings, it is a process to get approved. The testing that has to go into it, and the kind of quality control and assurances that it will meet all of the structural elements are very, very, very complex. That said, as soon as we can meet those, you can do it. There is scope for alternate design methods in the code. You can go through those processes. So as we get better and better at building these things, so this is like a 3D arm that can basically do, you can program in the work that we need it to do. And CNC machines are just absolutely incredible. And who knows what the future is going to bring. The ability to kind of innovate is incredible right now with our ability to incorporate modeling software. Most of the modeling software people are using didn't exist when I started in the industry. And now it's just, you're expected to be proficient at it already. So kind of the way things are turning around is just absolutely incredible. So who knows, this lecture might be obsolete because it's just the norm in 10 years. So that's your lecture on complex geometry. Next week we'll do our installations in street furniture and kind of small scale installations that don't meet the building code at all, and what could we possibly do for those things. All right.